Hello everybody, welcome back. This is the first in a two-part lecture on category theory. So over these two lectures we will explore some basic concepts in category theory, and there'll be some takeaways. And the first is that category theory de-emphasizes, how do you spell de-emphasize? De-emphasizes objects and emphasizes morphisms. Oh, I cannot spell today. Emphasizes morphisms. Most objects you've encountered before form categories. And universal constructions show up everywhere. So the first two lectures, the first lecture will mostly focus on these first two bullet points, and the second lecture will focus on this third one. So let's begin by talking about basic definitions. This definition will be motivated after I introduce it, and we can look at some examples. Okay, so a category script C consists of the following data. First, a set of objects written ob C. As shorthand, if little c is in ob C, we write that little c is in C and refer to C as an object of big C. Right? 2, for each pair of objects C and D in C, a set written hom sub C, C to D, called morphisms from C to D. And if F is in this hom set, we write either F colon C arrow D or C arrow labeled by F D. So this is meant precisely to evoke the notion of functions of sets or other sorts of objects that you must be familiar with in order to be following along with these lectures. Okay, and the final collection of data are, so for any objects C, D, and E in C, a function called composition. That is written as a little circle, and right now I will include the subscripts C, D, and E, but after we list one condition that these data are subject to, I'll be able to comfortably omit those subscripts because no confusion will arise. Okay, so we have this function C, D, and E, and this is a function that goes from the product of the Hom set from D to E with the Hom set from C to D, and it maps to the Hom set from C to E. And I've written the product in this order just to evoke the natural order of function composition. So this takes little g and little f to the composite g circ sub c d e f. All right, these are going to be subject to a few conditions. So these data are subject to the following conditions. All right. So the first condition, say condition 1, composition is associative. Let me write out in long form what this ends up saying, though it's a little bit clunky. All right. So for any C, D, E, I was going to say F. Why don't we say instead A, B, C, D? In C, the following diagram is commutative. So we can start with product of 3 Hom sets. So the Hom from C to D cross the Hom from B to C cross the Hom from A to B. Now there's one operation that we can do. We can compose the first 2 morphisms, and that will give us a map called identity, comma, circ sub A, B, C. And let me try and make this neat, but it's going to be a little bit tricky for me to draw. So this will act as the identity on the first factor, Hom from C to D, and it composes the second 2 and will give us Hom from A to C. And from here, we can just compose, go down to the Hom in C from A to D. And the second, on the other side, we could compose these 2 and have that act as the identity. So this will give us a map called circ sub B, C, D, comma, the identity. And that will take us to the Hom set from B to D cross Hom from A to B. And then we can, let me just make sure to label that, A, C, D. And then this is the composition A, B, D. All right, so we ask for this square to be commutative. So hereafter, or here on out, we just write circ for composition. And we'll make sure to check, making sure it's defined. Since you can think of the collection of all composition functors, composition functions, I'm getting ahead of myself, the collection of all composition functions as being a partially defined function on the set of all Hom-sets, on the union of all the Hom-sets. Partially defined because it's only defined when it takes in two functions that have compatible domains and codomains. All right, so that was the first condition. The second condition, which I promise is just a condition, it's not extra data, is for each C in script C, there is a distinguished morphism called the identity of C, and this is in the Hom-set from little c to itself, which we could sometimes write as endomorphisms C, and this is characterized uniquely by the property that that F composed with the identity of C equals F for all maps F from C to D, and the identity on C composed with G equals G for all maps G from, say, D to little c. So these functions act as the identity, as they should, given the notation. These are called the identity. You should check for yourself that the identity of C is unique if it exists. Hence 2 really is just a condition not additional data. Great, so that is the definition of a category. Let's go ahead and give a whole bunch of examples. The first couple examples are going to be maybe expected, but I want to make sure to give some examples that de-emphasize the notion of objects of a category being like sets, and instead emphasize the arrows, the morphisms in the category. So the first ones, let's say, there is a category called set, whose objects are sets, and morphisms are set functions. right, moving on, there is a category called group of groups and homomorphisms. All right. Furthermore, more especially, there is a category ab of abelian groups and homomorphisms. Now, let R be a ring. There are a number of categories. There are categories L mod R of left R modules, left R modules plus R linear maps, and here we write hom sub R from M to N as shorthand. Similarly, there is R mod sub R for right R modules and R linear maps. If R is commutative, we have just mod R, which, in a sense that I will define rigorously soon, this is equivalent to L mod R and R mod R. So left modules and right modules coincide over commutative rings, and this induces an equivalence of categories there. So to specialize, if K is a field, we write vect sub K, definition to be K modules. It's the category of K vector spaces. One other, in the same vein, if R and S are both rings, there is a category called RS bimodules. Whose objects are bimodules which are basically abelian groups M with a left R action and a right S action. And morphisms are, of course, abelian group homomorphisms oops, having a hard time spelling today. Homomorphisms respecting both actions. It happens to be true that category of RS bimodules is equivalent to the category of left modules over the ring R tensor S op. I may have gotten that backwards, but I think that's correct. All right, now here's an important example of a very different flavor. So let's have P be a poset, a partially ordered set, or more generally, a preorder. That is, a set equipped with a relation that is transitive and antisymmetric. No, that's not a preorder. A preorder is a is a set that comes with a relation that is reflexive and transitive, and a poset is one that furthermore is antisymmetric. Okay, so if P is a poset, there is a category also written P where the morphisms in P from little p to little q is, well, it's empty if P is not less than or equal to Q and consists of a single point if P is less than or equal to Q. So we view this as a category. For instance, we could have a poset that looks like this. And that can be our category. Hidden in this is that map, which is both the composite of these two and of these two maps, and then also all of these other composites like that. The one thing we can say is that a category can be generated by a graph. Okay, so that's a really, really important class of examples. Here's another interesting class of examples. So let G be a group. Then the category BG with one object and where the morphisms in BG from that object to itself are equal to G, with composition defined by the group operation on G. Composition of H or G is by definition equal to G times H. Cool. Let's have a couple more definitions. Let's have a category C. A morphism. I'm really having trouble writing today. A morphism F from little c to little d is called an isomorphism if there exists some G going in the other direction such that, well, first of all, the composite of G after F is equal to the identity on little c, and the composite of F after G is equal to the identity on little d. one thing that you could have in the back of your mind is a category is like a monoid with multiple elements. A monoid with multiple objects. In this example here, what I probably could have added beforehand is if M is a monoid, we can take Bm to be defined precisely as here, and that's more general than Bg for a group G. So category basically is a monoid with multiple objects. Then if every morphism in C is an isomorphism, then we call C a groupoid. And the slogan here is that a groupoid is a group with multiple objects. Since given any group can be recovered as the endomorphisms in Bg of the unique object, okay, so let's move on. Once we have categories, well, the whole idea of category theory is that we should shift the focus from objects to morphisms. So let's talk about what morphisms between categories should look like. Sort of as with many other examples throughout algebra, it will be some kind of set function or functions that respect the conditions of the category. Okay, so let's take two categories. Oops. That wasn't very clear. There we go. C and D be categories. A functor, get all your dirty jokes out right now. Functor f from C to D consists of, first of all, it consists of some data. So for each object C, an object f of C in D, and 2, for each function f from little c to little c prime, and let's say little c to little d, the function f of f from f of c to f of d. Subject to the conditions, well, there are two conditions that we had on a category. One of them was associativity of composition, and one of them was existence of identity morphisms. So that's exactly what we'll want to preserve. So f of the identity on C is equal to the identity on f of C. And 2, f of the composite g circ f is equal to f of g circ f of f. Okay. Let me throw in a definition that I should have made a little bit earlier. Just let C be a category. C op is the category where objects of C op are objects of C, and the Hom set in C op from little c to little d is equal, by definition, equal to the Hom set in little c from little d to little c. So it's just the category you get by reversing the arrows. So we have a different name for functors out of opposite categories. So a contravariant. Yikes, I'm still getting used to this writing on the iPad thing. A contravariant functor is a functor f from C op to D. Now the thing is, it's really just a functor from C op to D, because C op is a category, and we tend not to say it's a contravariant functor from C to D. So the terminology is a little bit sort of excessive, but what we can do is we can sort of talk about the variance of a functor. Does a functor preserve morphisms, or does it reverse them in a certain way? We have a whole bunch of really important examples of functors. And there will be more examples all over the place. Okay, so there's a functor from group to set that forgets the group structure. In fact, there's a series of functors. For instance, we could have L mod over a ring to abelian groups to group to monoid to set. So each functor forgets some structure or conditions. Okay. Given this is now a very important example. Given a ring homomorphism, R to S, so let's call this F. There is a triple of functors. The first one is called F upper star, and this is going to go from L mod sub S to L mod sub R. And what it does is it takes an S module M and maps it to the R module R, where you just compose with the map map F. This is called restriction, sometimes restriction of scalars. So that's one of the functors. You also have a functor f lower shriek. That's how it's read. It's an exclamation point. It's read f lower shriek. And this goes from L mod R to L mod S. L mod R to L mod S. And this takes an R module, a left R module M, to the left S module S tensored over R with M. So this is the relative tensor product. Relative tensor product. I'll just write that out. Relative tensor product. And finally, there's a functor f lower star that also is going to go from L mod R to L mod S. What it does is it takes a module M to the set of R linear homomorphisms from S to M, equipped with its canonical R module structure. And for that, I'm going to write an underline here. So hom underline of R means considered as an R module. In general, we will see hom underline of C show up in various places where we can somehow endow that hom set with the structure of actually being an object of C itself. Later in the course, we'll make that a little bit more precise in terms of enriched category theory. This is perhaps non-standard notation. In the actual algebra literature, you might see capital H hom sub R from S to M here. I like hom underline because it relates a little bit more to other concepts that will show up later in the course. So we can summarize these functors by saying we have L mod R, L mod S, restriction of scalars goes this way, that's F upper star. This functor is F lower star, and this functor is F lower shriek. These are related in being a sequence of adjunctions, and that's something that we will talk about in the next lecture. But you can think about what's the relationship between these three functors. You might be able to express it in terms of hom sets. Another important class of examples. So if P and Q are posets, a functor between their associated categories, F from P to Q, just remember we're not using any notation to distinguish between a poset and its associated category, is precisely a monotone function. So what does it do? Well, it's a function f such that f of p less than or equal to little q can be equal to f of p being less than or equal to f of q. Great. Now another example that you can convince yourself of is if G and H are groups, G and H are groups, then a functor between their associated one-object groupoids to be H is exactly the same data as a homomorphism. From G to H. All right. There are plenty more examples that show up all over the place. But for now, let's go up the ladder of morphisms even further, and we can talk about morphisms between functors. No, wait a minute. I need to give one more final crucial class of examples. So, let C be a category. A presheaf on C is a functor from C op to set. And sometimes this is called a presheaf of sets. You could also have a presheaf of abelian groups, rings, of R modules, vector spaces, of anything. You'll most likely encounter presheafs of sets in category theory and topology. You'll sometimes have presheaves of topological spaces. In algebraic geometry, you'll find presheafs of rings and presheafs of abelian groups all over the place. That's not what we're going to talk about right now. So unadorned a presheaf is a functor from C op to set. There are a whole class of really interesting presheaves. We can also say a co-presheaf, which is, a little bit of a clunky word. A co-presheaf is a functor from C to set. The prefix co tends to mean take opposite categories. We will see this all over the place. All right, so those are presheaves and co-presheaves. There are two very, very important examples. Sure. So let C be an object of C. There is a presheaf written H sub C, and this is defined by saying that H sub C of little d is by definition equal to the set of Homs from little d into little c. So, exercise prove that this is a functor. A contravariant functor. Dually, there is a co-presheaf in H upper C, and that's defined by taking Homs out of C. And another exercise is to prove that that is a covariant functor. We'll end up redefining this guy to be called Yo of C, Yo standing for Yoneda, but that will only be after we state the Yoneda lemma. That's coming up soon. Alright, so we have those really important presheaves. Let's move on to talk about morphisms between functors. So definition. Let's fix. Let's take two functors f and g from categories C to D. A natural transformation written alpha from f to g, but where the arrow here is a doubled arrow. The LaTeX command is \R, right arrow. So a natural transformation is some data. What are those data? Well, for each little c in C, a map alpha sub little c from f of little c to g of little c. And this is called the component of alpha at C. So those are all the data. We want these to satisfy, well, if f is a map from little c to little d, then the following square commutes. So we can take f of little c, and we could go down to g of little c via the component at little c of alpha. We could also go over to f of little d via f of the function little f. And we could do the same for the other half of the square. This would be the component of alpha at little d, and this would be g applied to little f. And so we want to ask for that square to be commutative. And ask for that square to be commutative. Great. There are two natural ways that we can compose natural transformations. By the way, we may sometimes express this picture as this kind of globular diagram. It's quite literally called a globular diagram. The definition, if alpha is a natural transformation from f to g, and beta is a natural transformation from g to h, and f, g, and h are all functors from categories C to D, we can form their vertical composition written alpha star beta, and this is going to be a natural transformation from f to h. Pictorially, this will look like we have g here, f here, h here, alpha and beta. No, I want to write beta star alpha. Well, what does this do? Well, the component at C of beta star alpha is going to be equal to the composite, the component at C of beta, the component at C of alpha. An exercise is to verify that this works, that this actually gives a natural transformation. Now, if C, D, and E are categories, F and G are functors from C to D, and F prime and G prime are functors from D to E, and alpha is a natural transformation from F to G, and alpha prime is a natural transformation from F prime to G prime, we can form their horizontal composition pictorially. What this is going to look like is we have C, D, E, should be an E, F, G, alpha, F prime, G prime, alpha prime, and we will take this to the picture where we have F prime composed with F, G prime composed with G, which means that this should be an E, not a D, and the natural transformation here is what we're going to call alpha prime circle alpha. So what is the component alpha prime circle alpha at C? Well, it's going to be a map from F prime circle F of C to G prime circle G of C. How is this going to work? Well, we're first going to use the component of alpha at C to get to F prime of G of C. And then we're going to use the component of alpha prime at G of C. Alpha prime at G of C to get us there. Great. So that's the horizontal composite. Again, an exercise is to verify that this works. Exercise. This works. Okay. Now, natural transformations are going to show up all over the place in our work over the next, well, I was planning things out, and just to get through the spectral sequences part of this course, it's going to be about 45 lectures total. Anyway, so a natural transformation is a natural equivalence, or is a natural isomorphism natural isomorphism if alpha sub c is an iso for all c. With this in hand, we can talk about two different notions of equivalence for categories. One of them is bad, and one of them is better. So categories C and so a functor F is an isomorphism if it is so in the category of categories. A functor F is an equivalence of categories if there exists some G. Let's fix notation and say that F goes from C to D, and G goes from D to C. If there is such a G such that the composite of G with F is naturally isomorphic to, but not equal to, it's naturally isomorphic to the identity functor on C, and F composed with G is naturally isomorphic to the identity functor on D. Now, the actual natural isomorphism there is data. It's part of the data. However, given any equivalence of categories, there is a way to extract sort of a canonical equivalence out of that. That is to say, any equivalence of categories can be promoted to an adjoint equivalence of categories. We'll talk about that in the next lecture when we discuss adjunctions. All right, now I want to leave you off with the most important theorem in category theory and one of the most important easy lemmas in all of mathematics. This is going to be called the Yoneda lemma. The proof is going to be left as an exercise because it is a proof that everyone should do exactly once in their life. It's not difficult, you just have to chase some elements around. Okay, so the Yoneda lemma says, let C be a category. Oh shoot, I should have let me hold off on this for a second. I need to go back up and introduce one final concept. Bear with me. So, if we have, let C and D be categories. Fun from C to D is the category the category whose objects are functors morphisms are natural transformations and composition is vertical composition. Then also, if F and G are in this functor category, we write nat from F to G for what could also be written quite clunkily as hom in this functor category from C to D from F to G. Okay, now that I have those bits of notation out of the way, we can actually state the Yoneda lemma. So, before this is called the Yoneda lemma. Let C be a category. Then let C be a category little c in C and F a presheaf on C. Then there is a canonical equivalence. Canonical bijection of sets between, on one side, natural transformations from the Hom functor h sub c, as was defined above, into F. This is in bijection with evaluating F on little c. So to say this is canonical, amounts to a natural isomorphism of functors that, well, what's their source going to be? Well, the source is going to be C cross functors from C op to set. I realize I haven't defined what the product of two categories is, but it's just the product on underlying sets and where homs are pairs of homs from the two categories. I take it that you can figure that out on your own. So these are going to be functors from this product category into set. And the first functor, well, what's that going to do? It's going to take a pair little c, comma f to the set of natural transformations from h sub little c to f. And the other functor is going to take the same pair, c and f, to the set f evaluated at c. And that is to say that there is a natural isomorphism there. I will leave up to you as an exercise verify all of the above. So, including naturality. Including naturality. Okay. A consequence of the Yoneda lemma, call it a corollary, why not, Toyota corollary. A consequence of the Yoneda lemma is that the functor taking C to the presheaf H sub C, so taking little c to H sub C is an embedding. In a sense that I absolutely should have defined earlier. So why not cover my tracks and give a definition? So let f be a functor from C to D. We say f is faithful if it's faithful if f is injective on objects, if f is injective on objects and morphisms, and f is full if in fact f is bijective on morphisms. We'll say that f is an embedding or fully faithful if it is both. The fact, which I will not prove, f is an equivalence of categories. If and only if it is fully faithful and not surjective, but essentially surjective, meaning that for all D and D, there exists some little c in C such that f of C is isomorphic to D, not equal, but isomorphic. It could be the case that it is, in fact, just a surjection on objects, but that's not always the case. Okay, great. So the Yoneda lemma amounts to saying that the functor H sub C, so H sub blank, the functor from little c to presheaves on C, is an embedding, is fully faithful, and we'll decorate it with a tail there to sort of say that it's injective in like the best way for categories. So we end up usually writing yo for this functor, and instead of H sub C, we'd write yo sub C, or sometimes yo of C. I prefer yo sub C because then if we want to apply it to an element, it doesn't get messy. So yo sub little c. That is the Yoneda lemma. Another upshot of it is that if little c and little c prime are such that h sub little c is naturally equivalent to h sub little c prime, then little c was isomorphic to little c prime to begin with. The slogan there is that to understand an object up to isomorphism, it suffices to understand how it relates to every other object, how it maps to every other object. Which allows us rigorously to say, let's take the emphasis away from objects and put it onto maps, and we can still understand the objects up to isomorphism. And remember that isomorphism is something defined by the certain types of maps in your category. So two groups are isomorphic if and only if they have the same, they represent the same Hom functors. This is where we're going to leave off for this lecture. Next time, we're going to talk about some other more important, super important constructions. So universal properties, limits and colimits, adjunctions, and con extensions. So I hope you'll tune in for that next one. Thanks for tuning in this time.